I'm going to talk a little bit about some road salt research that we've been doing here in Minnesota, actually for quite some time. As Allison said, my name is Andy Erickson. I'm a stormwater research manager here at St. Anthony Falls Laboratory, part of the University of Minnesota. We're going to talk about a number of projects we've been doing, although there was research prior to this work as well. So if you're interested in finding out more about that, we have a website, we have our publications on there. You can always contact me and I'd be happy to share other resources that we have. So I probably don't need to explain to this audience the chloride issue that we have. Chloride is a problem in cold climates. Wherever we use sodium chloride as part of our road salt and roadway management activities during the winter. We've seen the evidence of that in a variety of different ways. In the upper left here, we've got chloride impairments in high-risk water bodies in the Twin Cities metropolitan area of Minnesota. In Madison, water wells are showing up with road salt contamination. We also correlated lake concentrations of chloride with rock salt sales in Minnesota, but even in the Chicago area, we are seeing evidence of contamination in groundwater due to chloride from road salt. And these are just a few of the examples. There's evidence in a number of places all across the nation and around the world and in Canada of road salt and sodium chloride having impacts on the environment. And that's what we're trying to reduce or ultimately eliminate or avoid altogether. So I'm going to talk about some of the research that we've done towards that end. And I've organized this presentation in the form of kind of a top five things we've learned related to road salt. And I'm phrasing these, being an academic, I'm phrasing these in research questions. So the first thing we're going to talk a little bit about is, do we have a salt legacy problem? And I'll explain what that means here in a minute. But can permeable pavements be a means that we can reduce road salt? What about other chemicals and anti-icing agents? There's been some recent trends towards applying road salt or other chemicals before the storm to try to reduce our impacts of sodium chloride or other chemicals. And do some of those chemicals have environmental impacts? What are those environmental impacts? And finally, is there something else? Can we just avoid chemicals altogether? So we'll kind of close out the presentation with that. And this is just, again, a snippet of some of the research that we've done. We have a lot more that we could talk about. So if you're interested in continuing the conversation, I encourage you to do so. And let's keep the idea generation moving forward. But let's talk a little bit about this salt legacy problem that I mentioned. So we did some experiments to understand what was going on with sodium chloride once it got into the soil. And we were really trying to replicate the near surface soil, so the soils right alongside the roadways, which is kind of the first part of the natural environment that road salt impacts. And what we did was we tried to simulate what we called salt loading or snow melt, where we add chloride concentration to water that goes then through soil. And we used the three most common soil types in Minnesota. And the first thing we noticed is that not all the chloride from the road salt came out of the bottom of the soil. These were column experiments, so they're very controlled experiments in the laboratory. We do have field data. I'm going to show that on the next slide. But not all the salt came out when we ran these snow melt experiments. And that was very interesting. We're not the only ones to show this, so this is not isolated to this single set of data. There's other data in other places by other researchers that have shown very similar trends. What was interesting also is when we go to summer rain, this kind of freshwater rinsing, we don't see all the salt come out either. So these two plots are showing chloride concentrations over time or flow rate through the column experiments. And what was super interesting is when we loaded it, not all the chloride came out. When we put clean water through it, not all the chloride came out. So this chloride and the road salt is somehow interacting with the soils and not traveling 100% with the water, which has been the conventional wisdom and understanding of these processes for many years. But as I said, this is some laboratory experiments, column experiments. We also found the chloride is building up in our soils adjacent to real roadways out in the environment. We went out to a highway where we had really good salt application data for a number of years. We collected soil cores. We looked at that data in terms of depth and location, distance from the roadway, et cetera. Again, there's way more detail that you could see beyond this slide. The full report's linked here at the bottom, and I can provide links and even email attachments for all the resources that I'll share today, if you are interested. But this plot is really just showing depth below the surface at 4 different distances away from the roadway at 2 different sites. And if it's more red, that means there's more chloride in the soil. So we did see variations of chloride concentration in the soil based on depth and distance from the roadway, but it was not zero. So the salt is accumulating in our roads. It is building up in those soils. And what that means long-term is that we have a legacy problem in the soils. In other words, if we were to stop using sodium chloride 100% today, never used it again on our roadways, there is still a buildup of salt from the decades of application that has gone on in the past. And it may take years or decades for all of that salt to wash out again. That's what our rinsing phase experiment showed, is that it takes a really, really, really long time, a lot of water, a lot of very clean water to really flush out all of that salt from the soil. And that means we have a salt legacy problem. So what can we do to reduce the inputs to the soils? One question was permeable pavements. Permeable pavements are being used in stormwater management at the surface, not for chloride management, but for volume reduction and water quality. Other aspects, there's actually a number of benefits that you can see here on this slide: hydroplaning resistance, smoother riding surface, less spray, better visibility, noise reduction. Question we wanted to answer is, what about road salt? If we put down a permeable pavement, recognizing that that's a direct connection to groundwater, can we use that to reduce road salt or eliminate road salt applications? And what does that mean in the winter? What does that mean in cold climates? Are we going to have snow and ice and driving impacts by using permeable pavements? And so that's what we measured. 2 parts of this research. One was related to temperature. This plot is actually temperature profiles into the soil below a pavement. And it's going from the darkest color here at the bottom of these profiles. This is right near the surface of the pavement. And the lightest colors, very light blue that you can maybe barely see, are actually at about 18 inches below the pavement surface. And these are different temperatures over the month of about January 10th to February 12th. It happened to be in 2012. This is an impermeable asphalt residential site. It's a residential street. But 1 block away is actually a permeable asphalt site. And we had temperature sensors there as well. And what's super interesting is when you compare these 2 trends, when the weather is warm, when it's warm outside in the winter, it can be warm in the winter. We have snowmelt events in January and February. When it's warm, the permeable pavement at the same location, this is a block away, was actually warmer. It was roughly 5 degrees Celsius warmer on the permeable pavement at the surface when the air temperature was warm. But the opposite was also true. When it was cold out, the permeable pavement was actually colder. So we didn't really expect this. This is something, we thought maybe the permeable pavement would convect air as well as it, moving water. Why does it move air? If it goes down below the frost line, why can't the heat from below the frost line come up through the pavement? Not true. When it's really cold, the permeable pavement's colder. When it's warm, the permeable pavement is warmer. And what's also interesting is just in that 18 inches from the pavement surface to into that subbase, there's actually a temperature difference there as well. The permeable pavement had almost 15 degrees Celsius difference over that 18 inches, whereas the impermeable pavement only had about 5 degrees. So coupling this with what we just saw about warm and cold temperatures, the bottom line here is permeable pavements are actually insulating. They're just like insulation at the surface. So when it's cold out at the surface in the air, that heat below the frost line can't get to the surface. Permeable pavements actually prevent that heat transfer. It's also the same thing at the top. If you have a nice sunny day in January, really warm outside, that heat can't penetrate through the permeable pavement. It gets trapped. So what it means, bottom line, is these permeable pavements can be beneficial in some cases, but in other cases, they're not. We also measured friction. And so in addition to seeing thermal insulation, we saw that anytime it does melt at the surface, the water disappears. And we had sites where permeable pavement and impermeable pavement were right next to each other. And we can see pooling of meltwater on the impermeable pavement that then refreezes at night, causing an issue. Whereas on permeable pavement, disappears. Refreezing never happens on permeable pavement unless you don't maintain it. If you don't maintain your permeable pavements, you lose all of your benefits of having a permeable pavement. You can't just set it and forget it. You need to maintain, you need to make sure they're not getting clogged. You also need to make sure it's good permeable pavement. Some of the early permeable pavement installations, especially in Minnesota, the contractors just didn't know what to do with this stuff. And so we had issues not only with clogging, but poor installation and failures, and it just didn't work. Today, contractors know how to do this. There's a lot of experience, there's a lot of good guidance for contractors. If you need to educate your contractors in your area on how to do permeable pavements in cold climates, please let me know. I can point you to resources, I can point you to training, I can point you to people that have a lot of experience on how to do this really well. So there are benefits to permeable pavements, but when it's cold, it could be harder to get that snow and ice off that pavement. So what about other chemicals? What if we don't use sodium chloride at all? What if we look at potassium acetate or a formate or some other organic chemical to reduce our road salt, sodium chloride applications? Well, we did some experiments on this, and if anybody isn't familiar with what we call anti-icing, we put anti-icing chemicals down before the storm because what it does is it actually weakens the bond between snow and ice and the pavement. So when your snow plows come through, they actually get more of that material off. It can't freeze to the pavement and then just get stuck there. These anti-icing chemicals, which generally we apply 50% or so less when we apply it before the storm compared to when we apply it after the storm. So right there is if we use sodium chloride for both, it's a reduction right there. But if we use other chemicals, we could reduce it to 100% reduction, right? But that's really what we're trying to do is we're trying to weaken the bond so that the snow and the ice can't attach or adhere to the pavement, and our snow plows are just that much more effective. We wanted to measure these different chemicals to see which ones work best at this process. And we did it at varying temperatures. Just like we do in Minnesota in the winter, we turned the thermostat way down. We started at about 23 degrees Fahrenheit. Everything worked really well. And I recognize you can't see the data on the right side of this chart. You're not intended to be able to read it or see it. It's just giving you a visual that this data is available. It's in the reports, which again are linked here at the bottom. I'm happy to share this data if you want to dive deep into it. But at 23 degrees Fahrenheit, which is below freezing, everything works. Sodium chloride works, magnesium chloride works, potassium acetate works. We actually used Rain-X, which is a hydrophobic substance. You can actually put Rain-X typically on your windows or on your car windshield so that the water beads off of it. The thought was, why wouldn't we want water to bead off of our roadways, right? Actually, that weakens the bond between snow and ice as well in the pavement. But when we start turning the thermostat down, when we go down to about 5 degrees Fahrenheit, surprisingly, sodium chloride still worked pretty well. We think it's within the margin of error, but generally we say about 10 to 15 degrees Fahrenheit, sodium chloride doesn't work so well. But in our experiments, at least in terms of bonding strength and how strong the ice stuck to the pavement, it worked about as well as everything else. But when we get to 13 degrees below 0 Fahrenheit, sodium chloride did not help. It didn't do anything. It was no different than just plain ice. But potassium acetate and propylene glycol worked very well. Magnesium chloride did provide some benefit, but as you get down to about 31 degrees below Fahrenheit, mag chloride starts losing its effectiveness as well. So if we think about alternative chemicals and think about potassium acetate, propylene glycol, for anybody who doesn't know, that's what we put on our airplane wings when we de-ice airplane wings at airports. It's propylene glycol. Ethylene glycol is what we use for antifreeze in our cars. Ethylene glycol is highly toxic and hazardous. Propylene glycol is not so. It's not poisonous like ethylene glycol is, but it still has some environmental impacts. So that was kind of our next question is, what about environmental impacts? If we switch to a different chemical, do we trade a chloride problem for an acetate problem or a glycol problem? So we did a fair amount of research on this. We measured both the toxicity. We actually focused, though, on potassium acetate We had some funding, very specific funding from our Department of Transportation, Minnesota DOT, to look at potassium acetate because they were piloting potassium acetate in Duluth, Minnesota. And they wanted to know what are the environmental impacts, what are the best uses of this material, things of that nature. So we focused on potassium acetate, but we have some data on others as well if you want to dive into the reports. But in terms of potassium acetate specifically, we looked at a variety of different application methodologies, and we looked at the toxicity. Again, what you see on the right here, and you're not necessarily expected to be able to read this, but we did a bunch of different scenarios. And what you're seeing here is the data. When you see a kind of salmon colored bar on this plot, that's the toxicity level. Okay, so in some conditions, case 1, case 2, case 3, again, we can go into the details when we have more time. But under certain conditions, all what we see in the runoff, it's not getting anywhere near a toxicity level. But as you apply more potassium acetate on more different kinds of roadways or under different conditions, or in different situations with more impervious surfaces, you start to exceed that toxicity level. However, it's not the toxicity that we expected. We were investigating acetate, but acetate was not the problem. Acetate actually in general, and this was a collaboration project with Iowa as well, and they actually developed a model to predict how acetate would move and degrade through the environment. And they showed that actually, under most winter and snowmelt conditions, the amount of acetate we would put down is not a biological impact on our environment. It's not a negative biological impact on our environment. Potassium was actually what was exceeding our toxicity levels. So that's where we need to focus our next efforts. Is thinking about what can we use for alternatives. Maybe not even the acetate or the propylene glycol, but something in that formulation, something else in the formulation might be the toxic issue. And that's where we need to worry about it. And actually, we showed the potassium could be above toxic concentrations even when we apply it to 25% of the roadways. So generally, we recommend that we only put it down under the most precarious winter situations and driving safety locations. So only where you really have the biggest problems, and really probably on the coldest days. Potassium acetate also works at very low temperatures, so that's one of the benefits of it. But we really don't want to be putting it on parking lots. We don't want to be putting it on other roadways and driveways because these areas, they're unregulated. Most of the applicators are untrained. They're highly susceptible to over-application. And we just don't want to exceed any of those toxicity limits. We also need to think about the formulation here. And again, this is kind of getting into quasi-chemistry lesson, but we need to think about something other than potassium, maybe a sodium or magnesium or some other cation that would not exceed our toxicity levels when we want to apply it at the rates that we typically need to apply it to keep our roads ice-free. But one of the big pushbacks on using alternative chemicals is the cost. And most people say, well, it's just way too expensive to switch to potassium acetate or switch to something else. And we did the math. And there's actually a financial case to be made for switching. And that's what I'm going to share now in the next couple slides. There is an economic incentive to going to alternatives. So if we think about material cost first, because at the end of the day, that's the first thing anybody asks. Cost of road salt, again, these are ballpark numbers. And again, I can send you a resource here if you want to see how we got these numbers. But in general, cost of road salt, sodium chloride, this is rock salt, about $100 a ton. Okay, it's relatively cheap. But the vehicle corrosion, the road maintenance, the damage to trees, the damage to other infrastructure, bridges, concrete, etc. Pretty good estimates are out there to put that at about $3,000 per ton of sodium chloride applied. So the damage impacts are actually pretty considerable. If you think about the ecosystem or the environmental impacts, and again, this is where it gets a little more nebulous, a little more subjective, although there has been some really good literature on this and people putting cost to the environmental impacts of road salt, both on groundwater and surface waters. That's actually almost $10,000 per ton. So when you add these up, we're almost $13,000 per ton of road salt. And in Minnesota, there's been some different estimates over the years. Again, it changes every year. It depends a little bit on the weather, et cetera, et cetera. But just I think MnDOT alone, a pretty good estimate in recent years at least, is around 400,000 tons per year being applied just by highway DOTs. That's about $5.2 billion per year total impact, total cost of not only materials, but damage to infrastructure and vehicles, and ecosystem impacts. When we go to alternatives, if we think about something like potassium acetate, again, with the caveat that we need to find something other than potassium to use, when you think about acetate de-icers, they're about 16 times more expensive than road salt per ton. It's just the nature of being the chemical that it is. In addition to that, you're going to have to change. You have to have different equipment. So I understand and I recognize and acknowledge that the capital investment up front to switch from a rock salt or even a brine application system to a potassium acetate or other liquid de-icer, anti-icer alternative chemical, I recognize that that is a big upfront capital expense as well as ongoing material cost. I get it. It's 100% true. However, when you think about the overall damage to infrastructure, we're not talking ecosystem yet, just infrastructure, vehicle damage, road maintenance, all of these things actually are pretty minimal when you think about potassium acetate. Again, potassium needs to be switched, so let's just talk acetate for a moment. The impacts to infrastructure and the ecosystem are relatively minimal. So when you actually add that up, now again, acetate, potassium acetate, you do have to add about 50% more volume than you do sodium chloride for the same effect at temperatures where sodium chloride works. Obviously, potassium acetate works at temperatures much colder than sodium chloride, so maybe it balances itself out. But regardless, if we assume that higher application rate, again, 400,000 tons per year, we're a little less than $1 billion per year. So you actually save overall over $4 billion per year just for a single state's DOT application when you compare potassium acetate to road salt based on sodium chloride. So there is an economic argument to make. And this is substantiated by research, by literature, by economists. They have done this. We didn't just come up with these numbers off the back of an envelope. There is citable research that supports these values and these numbers. So if you need that to help make the case in your areas, let me know. I can give you these resources and these references. However, I also understand and acknowledge the argument that, keeping our roads safe, keeping them ice-free and snow-free in the winter is very important. It's human health and safety and public safety. I get it. So it can be a very challenging argument to make, even if you have the numbers behind you. But I feel like there is a burden of evidence here that we can move from sodium chloride to others. But what about other things? What if we don't want to do chemicals at all, right? We've all heard in the news about chemicals that we've made in the past that we thought were the next greatest thing. And sure, they were great and they served a wonderful purpose. And now we're finding, forever chemicals are a problem in the environment and in our human bodies. So maybe we don't want to trade one problem for another. So I always think about abrasives. I mean, ultimately, at the end of the day, we need friction on our roadways to be safe. We need our vehicles to be able to stop and maintain control in the winter. And in places like Scandinavia, Norway and Sweden, Denmark, they have other ways of keeping their roadways safe without using sodium chloride. They're using abrasives. They're using, they actually, in some places, they'll use chains on their tires or studded tires, but other techniques. I mean, they also have a different expectation in those cultures that, you know what, it's winter. There's snow and ice everywhere. Maybe we don't need to be driving at freeway speeds in the middle of the winter in a cold climate. So some of it's a little perception and expectations, but also there are alternatives to using chemicals. Some of the pushback to using things like abrasives, sand or grit, it doesn't work as well. It bounces off the road or it gets blown off the road. Some have argued it's more expensive than salt. I don't know if that's true or not. Even considering maintenance, I recognize if we put sand down on our roadways, it's going to fill up in our catch basins and in our stormwater pipes and our stormwater BMPs. But guess what? That's what our stormwater infrastructure is for. It's meant to remove pollutants, including sediment. And sediment is actually the easiest pollutant to remove out of our stormwater practices. It's the easiest in terms of maintenance. It might be costly because there's a lot of sediment, but it is the easiest. When you compare salt to removing salt from water compared to removing sand from water, there's no contest. There's no question. But a pushback has also been, well, what about all this sediment? Is it filling in our streams? Is it having more environmental impact? So let's talk about that a little bit. We're showing, and even we're really just going to answer the question. We only have time today to answer the question, does it work or not? Because many people say, well, if it doesn't even work, why use it? In places around the world, it is working very, very well. And actually, some of the new techniques can reduce how much sand we put down if we switch to 100% sand. And one of those techniques is what's called water heated sand. So again, data on the right, you're not going to be able to read it. It's in the report. It's just giving you an idea that there is a bunch of visual here that you can look at. What we did is we looked at a bunch of different temperatures and we looked at different pavement treatment techniques and measured the friction. How well does it work? What we learned, bare pavement obviously has the best friction. If you have a bare pavement, you're going to get the best friction. That's why many of our DOTs want bare pavement. That is their striving goal. But that's no surprise. We all know that. Bare ice is not safe. If you have just ice on the roadway, it's going to be slippery. You have a very low friction, or what we measured was friction coefficient. Again, no surprise. That's very obvious. It's as researchers, as academics, it's really nice when the data supports reality and what we all kind of know as common sense. But it gives validity. It shows that what we're measuring is representing what we all know to be true. So then when we go to things that we don't know and we're trying to answer research questions, we have confidence that the data is supporting the conclusions we make from that data. So the next thing, what many people, I don't know if many people are in the audience that remember this or have experienced this, but in many places, a number of years ago, we did it here in Minnesota. We used to put sand down, dry sand was put down on the roadways as an abrasive in the winter to help with traction. And again, many people said it didn't work. We had to put so much sand down because so much would just blow off the road or get sprayed up on the cars. It would chip the cars. It would fill up and plug all our stormwater pipes. Well, our research showed that actually, if you put down dry sand on top of ice, it's actually no better than just having the ice. You actually put the sand down for no reason at all. It did not improve friction. It did not help. And in fact, depending on the particle size of the sand, it actually made it worse. It almost was like marbles on ice, which is not a Disney show, but could be quite comical if it was. So then we looked at this technique that's been used in Scandinavia and other parts of Europe, Switzerland, for example, water heated sand. And the concept here is you take sand, you put it in a truck, and you actually put it in boiling water, essentially boiling water or water that's close to the boiling temperature, so that the sand picks up all that radiant heat. And then you don't put the water down, you just separate the sand and you put this sand down. That's really kind of at boiling water, boiling temperature. When it hits the ice, it actually melts into the ice a little bit and then refreezes. It turns that sheet of ice really effectively into sandpaper. And it works really, really well for increasing friction. It doesn't quite get the friction that you would get with bare pavement. I mean, no surprise, it's still ice with some sand stuck to it. But it's way better than dry sand. It's way better than bare ice. And it has way less environmental impacts than sodium chloride or even any of these other alternative chemicals. So water heated sand can work. I recognize, again, I acknowledge the cost to implement this here in the US is not insurmountable, and yet it's not easy. We have been working to try to get a pilot study down here, to get a truck over here, demonstrate that it works here in the US really well, to get cities to believe in the concept and get a city's perspective on what it was like to implement this. We're still working on that. If you are super excited about this concept and you would like to partner with us to become a pilot city to try it, I'd love to talk to you. Reach out to me afterwards. We'll continue that conversation. We've been pursuing funding to do this for a number of years and really just run up to the roadblock that many of the cities are just not ready or don't have capacity to try something like this yet. If you are, or you're at least interested in finding out, let's talk about it and see where we can go with it. So summarizing 5 things we learned about road salt. over the last many years, actually close to 2 decades now of road salt research here at the University of Minnesota alone. Do we have a salt legacy problem? Yes, we do. It is built up already in our soils near our roadways and in our soils feeding our groundwater wells. So we have a legacy problem. For those of you that might be policymakers, if we outlaw salt today, in 2 years, we're not going to see the benefits of that change. We might not see it in 10 years. We have literally decades of salt built up in the soil. So we should expect a fairly long time before we start seeing the benefits. But that means all the sooner we start, the sooner we're going to start to see the impacts. Okay. And if you're a policymaker, if you're in the policy realm, we can't have a policy that then implements today and then gets changed 2 years from now or 4 years from now. We have to have the expectation that this is going to take a while to see the benefits of our efforts. So we have a salt legacy problem. Permeable pavements is one solution. We can implement permeable pavements. They're not ready for the highways yet. They're not ready for the high volume, high load roadways. They're really good for residential streets. They're really good for parking lots. They're really good for driveways, walkways, things like that. They work really, really well. Just be aware that under really cold temperatures outside, and if you do have snow and ice there, that could be a little bit harder to get off than a conventional pavement. And we generally don't want to salt those pavements. So management there is a little bit different. However, and I should have added a slide. I don't have a slide made up for it yet. Permeable heated pavements are a thing. They are out there. They're working really well. There are some places where they've installed permeable heated pavement in their driveways. They sold their snowblower and their shovels. They don't need them. They never use them. Their pavement is always clear. Doesn't matter how much it snows or how hard it rains, freezing rain, none of that. It's gone. So permeable heated pavements are a thing. They could be the next best thing. So I encourage you to check that out if you haven't seen it. Anti-icing chemicals, potassium acetate, propylene glycol work well in terms of anti-icing. Potassium can be toxic at relatively low concentrations. So there are some environmental impacts we have to be aware of, and we do have to advance the science a little more, but the overall cost is going to be less with those alternatives than sodium chloride. But we can also look at abrasives. We could go to water heated sand or other techniques, heated permeable pavements, et cetera, that could really eliminate our need for sodium chloride in winter roadway maintenance. If this was interesting and useful and helpful for you, this is one snippet of some of the research we do here at the University of Minnesota, St. Anthony Falls Laboratory, and our Stormwater Research Group. We have an email newsletter called Updates. If you want to hear more, you can sign up for that Updates newsletter on our website, which is linked here. It's been on the bottom of every slide. You will also find our publications on our website. So all of the project reports, everything I linked to everything I talked about is linked on our publications page. So I encourage you to check that out if you want to dive deep. If you can't find what you're looking for, or you're not sure what to look for, reach out to me. I'd be happy to give you exactly what you need related to this research. I also want to just mention, Allison actually mentioned at the top, we actually had Laura Fay from Montana State University give our Minnesota Stormwater Seminar Series keynote presentation this spring. This is something we've actually been doing since 2019. Where we bring in nationally recognized experts on stormwater topics. Now, Laura Fay talked about road salt and chloride. We've had others talk about ecosystem services. We've talked about bioretention. We've talked about permeable pavements. We've talked about trees. We've talked about technology and real-time control systems. We've talked about monitoring, field monitoring. We've talked about street sweeping. So if these topics are kind of resonating with you in the stormwater world, or if you want to see things related to this, we bring in kind of conference keynote level, plenary session type speakers to give a seminar. And then we put them on a panel with local experts. And that's where Allison helped us out. She served as a local expert on road salt for Laura Fay's seminar. So we also kind of bring it down to earth and say, hey, you know what? I'm a regulator, I'm a city, I'm a municipality, I'm a consultant, I'm a watershed district, I'm a county, or I'm a state DOT, or I'm a state other regulatory agency. If any of those resonate with you or a nonprofit, those are the folks we have on our panel discussions so that they can connect directly with your real world challenges. So if you're interested in that, sign up for our seminar. We have a seminar actually next week featuring some research that was done here locally on iron enhanced sand filters. We also, every one of these is recorded and on our YouTube channel. So if you want to see that, I encourage you to just Google Minnesota Stormwater Seminar Series, and you'll find our website, you'll find our YouTube channel, and all of that. With that, if there's any time left, I'd love to answer any questions you have. And again, please reach out anytime. Thank you so much for your attention.
Excellent. Thank you, Andy. And we'll give people a minute or two because there's a little bit of a lag on the live streaming end. But I did drop a link in the chat to the St. Anthony Falls Lab website, and I was able to find the direct link to Laura Fay's presentation in that panel using winter chloride management to reduce the
Nice.
impacts of winter maintenance operations. Yeah. So those are in the chat for folks. And we do have one question that came in right away, so I'll ask that. And in the meantime, everybody else, like now's your chance. Please, you can type a question or a comment that you have. Like I said, it's always great to hear from the audience. But first question that we have for you, Andy, is what are permeable road surfaces made of? And how widespread, actually, I guess a few questions. How widespread are they compared to impermeable asphalt concrete? How much more costly are they?
Yeah, great question. So, number one, what are they made of? So you can actually get permeable asphalt that looks a lot like conventional asphalt. You can get permeable concrete that looks a lot like impermeable concrete, or you can use block pavers. So what you see actually on this slide, this like question slide here, are a block paver system. It is load rated, so you can get it for a number of different types of road surfaces. So there's really three different types: permeable asphalt, permeable concrete, and paver based or block paver based systems. These happen to be pavers made out of concrete blocks. They are generally, again, they can be installed just like you would conventional asphalt or conventional concrete. However, you do change the mix, and you do have to change the construction pace of it. I know in Minnesota, and I kind of mentioned this, we struggled at first. New Hampshire, I also have some experience from New Hampshire, also struggled at first with their contractors. So we have good guidance today. We have good specifications. If you're a municipality and you want to do this, we have good details and specs and guidance for how to do it well. That's kind of what they're made of. How widespread are they? They generally a relatively low percentage of pavement surfaces, I would say. Again, they're not used on highways at all, interstate highways. They are used in residential areas. They're used in parking lots. City of Shoreview here in Minnesota, it's in the Twin Cities metropolitan area. They're actually converting, whenever they're doing street reconstructions, the first option they look at is permeable pavements, because they've actually eliminated most of their stormwater infrastructure, because the permeable pavement does the whole job. So they happen to be in the Anoka sand plain. They have really good infiltration rates in the soils, really sandy soils. So they're converting all of their roadways to permeable pavements and eliminating all their stormwater infrastructure, and then not applying any road salt. So in that city, at least, it's becoming very widespread. I would say on average, probably, again, it depends on where you are. Again, Minnesota is maybe an early adopter, and we've had a number of adoptions. But anywhere from a couple percent to maybe even upwards of 10% of the impervious surface that's not highways is permeable pavements already. We have a number of installations. Even 4 or 5 years ago, we found over 20 places where we could do measurements. And that wasn't even all the places. That was just the ones that were good for our measurements. And then the last question was cost. So I get varying numbers on cost. It depend a little bit on where you're at. If the contractor is afraid of it, not familiar with it, they're gonna bid high because they can cover themselves a little bit. But I've heard anywhere from 8 to 10 times per square foot cost of permeable pavements compared to conventional pavements. I've heard maybe double the cost. So it does depend a little bit on where you're at, what you're looking at. The familiarity, if there's any other regulatory design engineers, even design costs I've seen be kind of expensive if the consultants aren't familiar or what to do with it. But other places I've seen them come a long way and really reduce that cost pretty substantially. So I think
Did
that was
you?
all the questions. Did I miss
Yep,
any?
yep. No, that
Cool.
was
Okay.
great. Yeah. Did you say that so Shoreview isn't using salt on their
Well, they
permeable
still,
roads?
yeah. So my understanding is they're not.
Okay. I
I
need
could
to
be wrong. I could be mistaken, but my
uh-huh.
understanding is they're not. They're moving to totally permeable pavements. They're in the Anoka stand plane, so it's very
Uh-huh.
connected to the groundwater. And I mean, they might be in places where they don't have the permeable pavement.
Yeah.
I don't
I
think they don't have 50% of their roads as permeable yet.
Yeah,
So
but the sections that are permeable, I
yeah,
definitely need to follow up with them because that would be a great, yeah, follow-up webinar. Get
yeah. Yeah,
somebody
and I
from,
can put you in contact with
yeah,
Public
their
Works
public
there. We
works
have
team.
really good champions there.
Excellent. Yeah. A couple of questions that I had,
Mm,
Andy, I know you mentioned acetates, but not
mhm.
potassium acetate. So CMA, calcium magnesium acetate, would that then
Yeah.
be something that you would recommend? I'm seeing you nod.
Yeah, so that's definitely something. So we didn't measure toxicity, so I can't say it's
Hmm.
better or worse, but that would be kind of the first alternative. And I know a number of places are using CMA already.
Hmm.
I just can't comment on the toxicity. Now, what I
Hmm.
can say is, and I think CMA was tested there. So Idaho, the Idaho Department of Transportation had a laboratory or has a laboratory where they've done toxicity testing for a number of road salt alternatives. And I
Hmm.
believe they were the ones they did, if possibly others as well, did testing on CMA. So that data is out there. The information is there. Um, we were asked to look specifically at potassium acetate, so we didn't pull
Hmm.
that into our report. But CMA would be the first thing I would look to as an alternative to potassium acetate.
Hmm. And then the other thing, when you're talking about sand, I just kind of wanted to
Hmm,
clarify for the audience because we do see in Wisconsin, in more rural parts of the state, like, I
hmm,
mean, different county roads, even, well, I'm not sure, I shouldn't say that about Dane County necessarily, but I do know a lot of counties that will use sand on their county roads.
that's great.
And um, I feel like sand, you said dry sand is worse, right? But that's on ice, right? Not necessarily
Correct.
on snow or some snowpack.
Correct.
And I think on one of your slides you had mentioned brine wet sand. And I did actually a couple
Hmm,
months ago go out to visit Richland County. So that's in the
yeah.
driftless part of the state in southwestern Wisconsin. And they do wet their sand with brine. And they
Yeah.
found that to be really beneficial to kind of like, I mean, the same idea with water heated sand, right? It's like you get it
Yeah.
to actually stick in there. And so you have that sandpaper grip. Of
Yeah.
course, it is still chloride, right? That we're putting down, but far less than if we were trying to, yeah, use
Correct.
salt to burn it off.
Yeah, and actually, Duluth, Minnesota also does that in some of their roads. They have
Okay.
some really steep roads, and
Hmm.
salt just doesn't work. So they are using a brine soaked sand as well.
Hmm.
And we thought they might be a really good pilot city to try this water heated sand, but they just weren't ready for it. They have a number of challenges they've been working through, and
Mm.
so they weren't ready to try it. But they're another example of a community that's been using brine sand essentially on their
Hmm.
roadways with good success and seeing pretty substantial reductions in total sodium chloride use.
Hmm. And
Absolutely.
yeah, probably sand use too, if that, by reducing that
Also
bounce and
true.
scatter.
Also true.
Yeah.
Correct. Absolutely.
So, all right. Well, those are the only questions. Let me just double check in. If any came in over email. I don't see any right now.
Okay.
So I think you're off the hook. Of course, some might come in a little later, but
Sure.
either if they come into me or directly to you, I know how to get in touch. So and everybody else does now as well.
That's awesome. Yep. Please reach
So,
out anytime. I really, really appreciate the time and the attention, the invitation to come and give this seminar and webinar. Super excited to spend this time with you and share some resources, and I hope it's beneficial. If there's anything else I can do to help, please let me know.
all right. Thanks so much, Andy. Take care. Be well.
Take care. Bye now.